Yeah. Yes. So this is, the first of the kind of discussion-y bits. There'll be some more talks after the break. My idea for this is to do what's called a fishbowl. So there are 3 seats in the fishbowl, of which we'll start with Patrick, Michael, and myself. And then if you would like to contribute in some way, like you want to contribute your own experience or ask a question or something like that, then you have to displace someone from the fishbowl. Try not to hog your spot in the fishbowl as well. But then it gives a chance to kind of focus the discussion, but with us in the bowl. And we'll if you've got my questions at the end of your slides,
Yes.
the questions to then sort of focus on once we've given these examples are about to appear on the screen, perchance.
Oh, it's not mirroring. Oh my God.
I will say the questions.
If you give me a sec. I don't know actually how to use a computer.
Yeah.
I've just been making mental notes of questions that discussions that didn't get answered. So if no one volunteers to go into fishbowl, I'll start nominating people. For example, Cyrus to continue that discussion about software resources as well.
Yeah, and if you could monitor the chat for it, thanks, Daniel. Yeah. Okay, so the kind of the fishbowl topics are about this, like sort of it's a chance to share any other sort of multidisciplinary initiatives that people are involved in, talk about how we can do multidisciplinary work effectively, how to get involved in such things, how do we support experimental work and publish results, and where do we divide between tools, practices, and staffing. So we're going to start in the bowl, and you're going to say a bit about those things, I think.
Patrick's going to lead off.
But these are very well-trained fish at the beginning. They have slides. So these are our discussants. So we as part of PROPL, we did ask for people to put themselves forward as discussants, which these fine people did. So thank you.
Yeah.
One note, if once again people could sort of move into the middle so that people are coming in the
Yeah, squeeze in.
Cool. Yep. Thank you very much. My name is Patrick. I'm a PhD student in the Department of Computer Science at the University of Cambridge. For the last 2 years, 1 year as a research assistant and 1 year as a PhD, I've been working with a bunch of ecologists and plant scientists on avoided deforestation projects. So the idea here is to look at avoided deforestation projects in the tropical moist forest region, so that's near the equator, and decide how much additional carbon is actually in these projects as a way to kind of work out just how effective they are at actually trying to keep trees there. Of course, there's a lot more besides just carbon. There's things like livelihoods, there's things like biodiversity, as we've seen today, but this is one thing that we're looking at to try and do quantitatively. What we want to show here is like some of the pain points that we struggled with that maybe are obvious, but also not so obvious until you're actually doing the coding and you're just a computer scientist trying to understand the ecology, but also do good computer science at the same time. So on the right here, we've got a visualization of some of the analysis that we do. It's a counterfactual scenario. So the points in green are an avoided deforestation project, and then these are matched to other areas within the country that are supposed to be very similar for some set of matching variables. And the idea here is that we can project kind of through time just what's happening outside the project and then compare it to what's happening inside the project. And hopefully what we'll see is that the project's actually doing a good job at keeping trees there, and so it has additional carbon. And the graph on the left is supposed to show these trajectories at the point where the project starts, and we see that the project is hopefully being additional, and unfortunately a lot of the rest of the country is losing trees, which isn't that surprising given how much deforestation and things like that are happening. To try and be quick about this as well, I'm just going to go straight to one of the problems that we had, which was that in order to do this analysis, we need a bunch of data sets. That can be things like accessibility maps, which are kind of these proxies to just how close are you to things like roads or cities. It can be things like elevation maps. We want to have pixels that match on each other that are kind of at the same elevation, because that impacts things like what trees grow there, what biodiversity is there. And then one of the other ones is land use class. So that's basically saying, is this area of forest deforested? Is it undisturbed forest? Is it degraded? Is it regrowth, water, or something else? And so these maps, the two colors to really pay attention to are kind of mostly green and mostly orange, and what they mean. So green is kind of forested, the dark green is completely undisturbed, and then that moves through degraded and regrowth. And then orange is deforested. And so the two images are for an area of Indonesia in the year 2008. But one of them is downloaded in the year 2021, and one is downloaded in the year 2022 from the same URL. And hopefully you can tell from the two that they are not the same. And in fact, the one on the right, the newer version, has a lot more deforestation in this area, in this particular area. And so the problem here is that the URL that we get these from is not necessarily versioned. And the backstory to this is quite anecdotal. My colleague Michael and I do a lot of work together, and we were trying to work out why we weren't getting the same numbers for exactly the same code running on exactly the same data. And of course, we weren't running on exactly the same data. I had downloaded some data, put it somewhere. Michael had used some other bit of data that we downloaded at some other time. And it took us maybe a week or two to work out, actually, our inputs just weren't the same at all. And so there's two kind of problems there. One is that where we were getting the data from wasn't necessarily versioned or easy for us to check if it was versioned. And then the tools that we were using, which is just the shell and Python scripts, weren't telling us anything about that either. They were just consuming the data and giving us outputs, and we were just trying to compare offline or over Slack or whatever kind of communication you use, and that ended up wasting a lot of time for us. Again, I think this problem is probably quite obvious, but not to us until we kind of started doing this analysis, and it's one of those things that I think within the computer science world, we're quite good at thinking about version control, things like Git and these sorts of things, but versioning big data sets is quite hard. And it's kind of an area that maybe requires a bit more focus from us. Another thing is that the complexity of these pipelines is huge. And I think computer science offers a way of making them even more complex than they ever were. It's easy to write more code and run more analysis and put more data in and add more layers and do more things. And trying to get some kind of grasp of this complexity and what kind of uncertainty is compounded through different versions of data, different versions of code, different versions of libraries, all these things over time becomes very, very difficult, and we can do a lot better, I think. And we've certainly struggled with trying to get a grasp of these problems, and hopefully we're trying to build some tools to make that a little easier.
I mean that was what led to my question earlier. Actually, was the, and I actually have an equivalent slide. But so this is our code and all of its dependencies, but they're all not just our software; they're many software. So yeah, so I have a similar story to tell. So I worked with another group of ecologists. This is for the life metric that Drew mentioned earlier, where we're trying to calculate biodiversity, the impact of biodiversity in landscape change. And I was acting as a sort of kind of embedded software engineer in the team. So I'm both trying to pull out research ideas that we might work on to help improve things, but I'm also just there to get the job done. And kind of this one is kind of fascinating to me because I was brought in because they were struggling. And on the surface of it, the core algorithm, an area of habitat calculation that is a kind of key point in a lot of these biodiversity analysis. This is a standard technique, well kind of represented in literature. You're taking that range that Drew was on about, like where the species might be found, and you can turn that into a binary layer. It's a lot of ones and zeros, and then the data you get also, the elevation an animal will typically be found in. So I can take a high resolution elevation map and turn that into a binary layer where the species might be found there. And I can do similar for habitat maps. And then you just multiply those three layers and you get a result, right? So that algorithmically is really simple to think about and kind of, it trips off the tongue very easily. But where it falls over is just the scale. And the ecologists were just couldn't get it to run in a real. When I joined, they were taking about a month to do all 40,000 species that are on the IUCN Red List. And we got that down to days by understanding computer systems, right? Like just understanding like this map is 150 gigabytes, this map is 150 gigabytes, right? These are like not trivial amounts of data but they look like images, so we can treat them as if they're trivial data. But computer systems tend to fall over when you throw that much at it. Like Linux will just do the out-of-memory thing and shoot your process. Then kind of another example of kind of where friction occurs is this is the pipeline for life, which is kind of similar to Patrick's, but this isn't in a CI system, right? There was a comment we got on Discord, was like, how does this kind of map to CI? What happens here is that Alice will edit this script and generate that result, and then Bob will take the next bit, but he can't get it working, so he'll pass it to Carol. Carol will do some edits and generate a file. That goes back to Bob, and then Alice doesn't even know Carol was involved, and just across this, right? And that's fine when you're doing experimental, we don't know what's going on, but when you're trying to make publish results that will inform politicians, that will have impact on actual, do we cut down a forest or not, that's scary to me, right? So, and then, I'm not going to go into detail. I think we've all kind of seen floating point number errors. This is real, right? So these hit us. And why do we have to have kind of, computer details propping up that we expect ecologists to deal with? So as a kind of interdisciplinary thing, it's fine when you've got this kind of, it's not fine, right? I don't scale. You can't put me in every ecologist project. And I think the challenge to some degree for us is how do we scale us to help those that are actually trying to do the labor to save the planet? So that's my bit.
Great, thank you. I think this is working, yeah. About 10, 11, 12 years ago or something like that, I was having conversations with various earth scientists in Cambridge who were talking about their code, and they were saying, we're a bit worried about bugs. It's quite hard to squash out all the bugs. And I said, there's an entire field of research right there waiting for you. Let me show you this thing called COC. All of these amazing tools that have been developed in our community are just not really accessible to people in, say, climate science. So what we started about 10 plus years ago is developing static analysis tools for Fortran. Fortran is the lingua franca of global climate models, of large-scale climate models for sort of historical reasons. But it's okay because Fortran is like a nicer version of C, at least, with an effect system and first-class arrays and things like that. So the project was really just looking at, well, can we build targeted verification tools that are very lightweight, don't have to understand logic, higher-order logic things, stuff like that. So that's how I sort of started getting involved, and we talked to lots of scientists around the place and looked at kind of some of the things they were worried about and some of the kind of specifications we could develop. So we developed that tool, and it's kind of ongoing. It got deployed at the Met Office for about a year or so on their big model. We had a knowledge transfer partnership where we had a postdoc who went and spent some time with them. And that kind of snowballed into what I do now. And I guess my prop is just this logo. So we have this thing at Cambridge called the Institute of Computing for Climate Science. And it's a multidisciplinary institute, mathematicians, computer scientists, machine learning, software engineers. And we work with 6 large climate science projects around the world. We have software engineers who are sort of embedded in working with those teams. And then we have the sort of research side looking at the problems that come out of that and thinking about how can we build programming language systems and tools to support climate scientists for the years ahead. So Rowley is part of that as well. So one thing led to another, I suppose, and it's nice. It's been a nice environment to learn from what climate scientists are doing.
And so a common thread here is that we're all stumbling into these multidisciplinary things. So what now? It's time to kick some fish out of the fishbowl. Would anyone like to, not me, would anyone who hasn't spoken yet like to step up and reflect on some of these questions and perhaps talk about some of the multidisciplinary things you're involved in or any other part of the question here, really? Come right ahead and come right in the middle here. I'm going to try and hold everyone to about a minute, so we can we have time for a few people to come in as well. So don't be offended if I start kicking fish out. And also, please do just introduce yourself briefly and give your affiliation.
Yeah, hi, I'm Martin Lester from the University of Reading. One project that my university has had is what they call the Open Research Champions, where they try to promote open research, so open access, but also the reproducibility across all kinds of disciplines. And that's been reasonably successful. But what I actually wanted to tell you about is that we're hiring lecturers at the moment. So,
excellent.
If anyone wants a job on
He's a shark.
I'm in.
Environmental science or whatever, we're a mid-ranking computer science department, but the university does host a very prestigious and successful meteorology department. So I think it's ranked 5th in the world, and we were top in some sort of people and climate league table recently. So if you want a computer science lecturer job, doing computer science, but in some kind of area like this, please do come and speak to me about this at the end of this session.
Thank you. Now, I'm actually going to volunteer our AV chair because I was hearing about some really interesting work on computing and climate science education. So, Caroline, please come in.
Hi. Okay, my name is Caroline. I have a bit of a complicated bio. In short, I do English literature, I do climate impact research, and I do programming languages. So I'm going to skip the history behind that. But I volunteer with a nonprofit organization. We're called Climate Science. You can find us on climatescience.org. And what we do is we are an educational nonprofit, and we create learning materials all around climate science, about the science behind it and not behind the politics, even though, sometimes it's difficult to draw the line, but we talk about the science and we talk about impact of policies, of course, as well. And our approach is that it is supposed to be accessible for everyone. So we do not assume any specific knowledge. We do not assume that the reader knows scientific language. We try to make it interactive so that, you don't have to just read a long text, black on white, and we're almost completely volunteer run. So I think, thank you for pulling up the website. It's been around for 3 or 4 years. Actually, it was founded by an undergraduate student at Cambridge. Climatescience.org.
I can't see what I'm typing.
Yeah, exactly. So if you click to learn, or maybe I can also.
Yeah. Oh, it's really hard to drive this thing. I'm getting out.
It's mirrored. Oh goodness, this is gonna be. Courses. So we have a bunch of different courses on different subjects. And for example, if you look at the food and farming course, we then have subsections. I'm sorry, I'm not sure this is working. We have more subchapters looking at different things, for example, genetic engineering. And what is our strong point is that we don't want to register. Oh goodness, I think I'm just going to talk. I think this is faster. What our point is that all of our context is peer reviewed, all of our content. And we do yearly quality assurance. And if you see a text on our website, you cannot see it now, but there's a lot of blue links in there, because every single fact that is on our website is either cited from some UN website or from a scientific research paper. So if you want to get involved in this, I'm a volunteer with them. We're almost completely volunteer run. Reach out to us. That's it. Yes.
Does that experience does that experience give you any? Oh God, bloody hell! Sorry. Does that experience kind of give you any kind of things that, if you look at this community, you think, oh, if only that was solved, this would be so much better getting out.
I think what is I think what is sometimes difficult is finding the right sources, because the way you sort of go on Google and you're like, oh, I want to write about this specific form of carbon emission in this industry, and then you have to find the right papers. So I think what would be helpful from, for example, institutions such as 4C, that we can just go to the website and find the papers, and that they have abstracts that are very informative and sort of explain what is going on in not too technical language, so that you can find the right papers. And then if the paper is, of course, difficult to read, you at least know that the effort you put into reading it is worth it, because you've arrived at the correct, information.
Thank you. Patrick.
Yeah, it's fascinating. So these are the things I think are extremely important, because if you look at the science of climate change is always sort of more or less settled. Of course, we don't know details and so on, but we know that stuff are going in the wrong direction and we need to change a lot. So getting the public or the general understanding of science at a higher level is very important, especially for democracies, because you have to vote for the next government and so on. So nobody will take sort of daring decisions on changing things. But so it's great stuff. I was going to mention another kind of thing which is related to this, which is I've been working with the Potsdam Institute for Climate Impact Research for a number of years, and there will be a talk a bit later by my collaborator Nicola Botta there. But I just wanted to mention that one of the interesting challenges from a programming languages point of view is when I got first pulled in, they wanted to talk about coupling models. And I thought, well, okay, you take two models and you put them together. That's nothing very strange. But the thing is that the models are of very different type. So you can have an Earth system model or an ocean model or something like that, which is like basically physics. You integrate over time some differential equations and you get the time series of data. And then the economy people, because they wanted to couple this to a good model of economy, they say, oh, well, we'll describe the state of the world as one time step per month, and when they have a vector of the next 10 years, that's 120 elements, and then we optimize our equations and we get, poof, the trajectory. So it's not integrating anything, it's just finding the optimum vector of states of the world or something like that. And how on earth do you couple these two systems? Because they're sort of a completely different kind. And also, I mean, sometimes you have probabilities involved, you want a monadic result perhaps. So there are all of these different ways of modeling things and just connecting them together. So I think that was I mean, I don't come here to say what solutions we have for it, but I'm just saying that that's an interesting aspect that I think programming languages research can come in and be useful.
Well, I was just going to propose Sylvie to comment on, just from the verification perspective, but
yes, absolutely, and that's like still a challenge even amongst like just climate science itself, because people want to move bits of models around between other models. So classic thing is having a subgrid model of some process, and you build it in one place and you want to move it into another model because you think, oh, this is actually a really good model of precipitation, and actually there's still a lot of challenges around that.
Yes, that's not one thing. So this is, of course, I knew about all the kinds of problems you have when you have different grids, for example, or different time steps. And those are sort of challenging by themselves. But this was sort of like, it tickled my brain because it was a kind of mismatch between models of a completely different level. They were sort of the wrong types completely. Anyway.
yeah, so Vashti, then Sylvie, and Patrick, you can rotate out.
Oh, okay, so I worked across disciplines, many different disciplines, including biology, and right now this is probably the start of interdisciplinary work across climate science, I hope it is. And one thing that I have been experiencing when dealing with data provenance is everybody says data provenance is really, really important, but nobody has any time to spend on providing the information for it. So I'm talking to Earth observation people at the National Physical Laboratory because they have weird data sets that get changed. They go back in time and change their data sets, and there seem to be major issues there. So hopefully they will have time to actually talk about data provenance, but this is a stumbling block that people think provenance is important, but they don't put any time into it.
I wasn't ready to be fished, but it seems I had no choice. So no problem. My name is Sylvie Belder. I'm a scientist in France, and I've been working with mathematicians for a while now, nearly 20 years. And I have two things to say. I'm also a floating point expert, so I was not surprised by that thing. But people get surprised that 0 is not 0, something like that. It's not, computation are not correct, and so you don't get what you expect. And so for reproducibility in particular, it may be very complicated. I had friends who had the same program on the same Java program on 2 different architectures that wasn't giving the same answer, so that's real problems. But I wanted to talk about the first one, what multidisciplinary initiatives are people involved in, and I've been working with mathematicians, and one thing that nobody spoke about is that, you know, speaking with people of other domain, it's hard, because they don't speak the same language as you are. So I've been thinking this morning that we spend a lot of time and energy to teach computer science to people who are not taught computer science. So there are examples this morning that people are programming for 10 years, but they don't have any computer science learning at the beginning. So maybe we should think about teaching computer science. That's all.
I'm Benjamin Pierce from University of Pennsylvania. I would like to advertise 2 things briefly. We have Penn is part of a multidisciplinary effort going on, starting up in the United States, hopefully with fingers crossed, with funding from the National Science Foundation, a group of programming language people, that's me, and architecture people, and machine learning people, and economists, trying to understand how to model and optimize trade-offs between operational carbon in computing and embodied carbon in computing. So this is approaching the problem of minimizing carbon footprint of computing in a sort of holistic way. If people are interested in that, I would love to talk to you. The second thing I would like to advertise very briefly is there is a large overlap between the computer science community and the board gaming community. And those of you that are interested in board games or willing to be and have not yet encountered this one should look up Daybreak board game.
That's this evening sorted, all right?
All right, done Daybreak first. So one thing we talked about collaboration in the Hazel setting, but I think more broadly, you can see this room is full of people that are interested in this topic. We all have friends that want to get involved in climate science organizations. So there's like a huge amount of interest in helping fix this big problem that we face as humans, right? And I think it is really hard to get involved in ways that actually leverage the individual skills of all of the people that we know, right? It's easy to go join an organization and maybe go to a protest, and that's very valuable. But all of these people that know a little bit of data analysis, that can do a little bit of data journalism, that can advocate for ways in which we can make our conferences more climate friendly, right? If you could do a little bit of data journalism and say, if we change our menu to be vegetarian, this is what impact it would have, right? My vision is really for that to be as easy as it is to go and edit a page on Wikipedia, okay? Like, I think that is what we need if we want to leverage the collective abilities of all of the people that care about this problem. Yeah. It's actually really interesting that you mentioned that particular example, because I am part of a student activist group, and one of the things that we have so much bike shedding over is what would be enough in terms of actions. And some people say we are going too far in what we're advocating and we're worried about backlash, or some people say that, oh, this small step would be enough. And if we could have access to the university catering services data, link it up to some sort of standard food emissions and run through different counterfactuals and go to the university and say, look, you're not living up to your own principles, that'd be super important. I came into the Fishbowl to talk about 2 slightly related things. One is, I did an internship at a major software engineering company over the summer at Meta, and they have a very interesting approach to programming language engineering, which is very much developer-oriented, and it's kind of businessy, but I think here it makes a lot of sense, which is who is your customer, and what skills can you use, what of your skills can you use to solve their problems. Of course, if you tell this to a bunch of people who are hired for their research jobs, it's a bit humbling. But I think there's something valuable to be learned there. And they're approaching it with, okay, what are developer efficiency metrics that we can use? And maybe it's a bit ambitious, but that would be a really good guiding star, saying, okay, what's the sort of productivity metrics that we expect for research climate scientists or other fields like pandemic modeling and prevention. And the second thing is, from a personal experience, I'm coming to the end of a very productive, hopefully, a PhD in programming language theory, and I've enjoyed it, but I'm looking to pivot at this point. And we probably really want to think about pipelines. I think the latent demand is very much there, but if we have summer schools and 8-week programs or longer programs, and we have the gradations, then we can nurture that talent without necessarily expecting it to just show up at your doorstep, so to speak. So anything which nurtures a good pipeline and has that, obviously it takes a while to organize, but something is better than nothing, and then that can be improved upon.
Do you mean a pipeline of people from our community? And very quickly.
Oh yeah, I think right. Well, sorry, I just wanted to clarify. Do you mean like pipeline of people from our community into ecology, climate science, or the other way? Or I just want to clarify.
Yeah, I think I mean just general. You know, you got your first year computer science graduates. Most of them come because they've realized that programming, the pay to effort ratio of programming is actually pretty good compared to other jobs. But you know, some of them also have a heart, and they're just there because, okay, this is interesting, it's a well-paid job, but if you can kind of reach to them and say, look, you can also do other useful stuff. Yeah, there's communities, and I can speak about this more kind of in the break, but there are other communities who've had a lot of success with this sort of model, saying, look, if you care about this particular issue, you don't worry about your background. We will give you the base training and contacts, but we just need your interest to come on and sign up.
So, continue this discussion in the break. It's been wonderful to hear so many voices from the audience talk about this. And we have, in the wrapping up session, we've got half an hour for us to figure out concrete actions and plans and how we can start pooling our resources. So I think this is a great kind of starting ramp for us to figure out what we're going to do next. So for now, into the break, and then we'll go into the final session in about 25 minutes. Thank you all. Thank you, Tony. Thank you all.